Hello, Math Humans. We're going to do our last section of trig in this particular chapter. We're going to do even more trig formulas. So our objectives are that we're going to manage the double angle, the power reducing, and the half angle formulas with the purpose of finding exact trig solutions. So I've written all of them out, and I would recommend highly that you copy them all down. Remember again that they are in the front of your textbook, so it is nice to have a complete and concise location for all of the identities and formulas that we have learned in this chapter. Alrighty, the double angle formulas are written here. The power reducing can get to be rather entertaining, and we'll talk about this as we go through some examples. The half angle formulas, so notice that they are all, at least for sine and cosine, plus or minus, and I will tell you that the sign that you're going to use, either the plus or the minus, let me scoot this up just a little bit, is going to be determined by the sign, SIGN sign, of the original angle. So we're going to go through and do a series of examples about each of these new types of formulas. So you can pause and write them down, or you can copy them out of the front of your book. Your choice. So let's jump in with our first example. And this one's going to say, find the exact solution. So all of the formulas help us to find exact solutions when the problem might not be given, where an exact solution is apparent. So in this one, I'm going to have 2 cosine x plus the sine of 2x is equal to 0. So if you'll notice, 2x is one of our double angle formulas. So I'm going to use that to help me rewrite this. So 2 cosine x plus, then my double angle for sine is 2 sine x cosine x is equal to 0. Factoring is my favorite F word, so I'm going to take out a 2 cosine x, and I'm going to get 1 plus the sine of x is equal to 0. Now I can set my two baby equations equal to 0, and I'm going to get 2 cosine of x is equal to 0, and 1 plus the sine of x is equal to 0. In this one, I get the cosine of x is 0. Cosine is 0 at pi over 2 and 3 pi over 2. And then in this one, I get the sine of x is equal to a negative 1, and that happens at 3 pi over 2. This answer is redundant, so I'm only going to report it once, and I'm going to write pi over 2 and 3 pi over 2. So I used the double angle formula to help me simplify this trig equation. All right. Example number 2, to try to switch colors of pens, I'm going to be given that the cosine of theta is 5 over 13, and it's going to be in the quadrant 3 pi over 2 is less than theta is less than 2 pi, and I want to find the exact value for the tangent of 2 theta. Oops, that's a theta. So the first thing that I want to do is I'm going to manage this. So this, oops, my bad, that's a 2. This tells you that it's between 3 pi over 2, so this tells me that it's in the 4th quadrant. So I'm going to draw that picture. Here's my triangle, and cosine is 5. This is 13, so that means the y is a negative 12 because it is a Pythagorean triple. So the tangent of 2 theta is going to equal 2 tangent theta over 1 minus tangent squared theta, and that's one of our double angle formulas. So then I'm going to do 2 tangent. The tangent of this is, sorry, I should have written, the tangent is a negative 12 over 5. It's going to be multiplied. And then I'm going to divide by 1 minus my tangent squared, so the negative 12 over 5 quantity squared. So in the numerator, I'm going to get a negative 24 over 5. And in the denominator, I'm going to get 1 minus 144 over 25. Okay, because 12 squared is 144, 5 squared is 25. I need to simplify, so I'm going to put my fractions together. So I'm going to turn this 1 into 25 over 25. So this is going to be a negative 24 over 5 over 24 minus 144 is a negative 119 over 25. I have a fraction divided by a fraction, so I'm going to multiply by the reciprocal times a negative 25 over 119. Okay, 5 goes into 25 a negative 5 times, and when I do that math, a negative and a negative is positive, and I'm going to get 120 over 119. I'm looking for an exact value, so I'm going to stop here, and I'm going to report that the tangent of 2 theta is 120 over 119. Okay, so that wasn't so horrible. All right. The next one that I want to do, so for example number 3, we're going to rewrite the sine of 4 to the 4th of x as a sum of first powers. Okay? So basically we're going to take an expression and rewrite it, and we're going to use our power reducing formulas. Okay? So I can write the sine to the 4th of x as the sine squared of x quantity squared. The sine squared power reducing formula is 1 minus the cosine of 2x over 2, and then I'm going to square it. Okay? So this is where our math is going to get entertaining. The first thing that I'm going to do is I'm just going to square everything. So the top is going to be squaring a binomial. So I'm going to get 1 minus, square the first term, multiply these two together and double it, 2 cosine 2x, square the last term plus the cosine squared of 2x. We're going to have to do it again, over 4. And to make my math life easier, I'm going to pull this 1/4 out front. So I'm going to write this as 1 over 4 times 1 minus 2 cosine 2x. Now I have to manage the cosine of a power, right? So I have cosine squared. Well, cosine squared is going to be 1 plus the cosine of 2 times the angle that was there, and then over 2. Okay, so I'm going to simplify this a little bit. So here's the 4th, and I'm going to write 1 minus 2 cosine 2x. This is going to be plus, I'm going to split it up into 1/2, and then this is going to be plus the cosine of 4x over 2. Okay, so it's nice to simplify this a little bit. There's not much that I can do. Okay, I could do 1 plus 1/2. So here's the 1/4, and then I'm going to have 3/2 minus 2 cosine 2x, and then plus, I'm going to write this as 1/2 cosine 4x, and then I would tell you to stop there. Oftentimes the book will go further, and they would multiply this by 2 over 2, and then they would expand everything, but I will tell you that I think this is a great place to stop. All right, I have one more example for us. We're going to do example number 4, and this one is using our half angle formulas. So that way we will have done an example from every different type of formula. So this one says find the exact value of the cosine of 75 degrees. Now, in a former problem in a section, we tried to do this with a sum. This time we're going to do it with our half angle formulas. So 75 times 2 is 150. So and this is a special, so I'm going to write this as the cosine of 150 over 2. And so that would be a half angle formula. And I'm going to write the original formula, x over 2 is going to equal, and then it's plus or minus, and then 1 plus the cosine of x over 2. So we're going to look at the cosine of 75. The original angle, 75 degrees, is here. Cosine and sine are both positive, so I'm going to use only the positive root. So the cosine of 150 over 2, because technically that gives me 75, is going to be the positive root, and I'm going to have 1 plus the cosine of 150 over 2. Now I need to do my 150. 150 is here, so it's 30 degrees shy of 180. This is 1, negative radical 3, and 2. So then inside my radical, I have 1 plus the cosine of 150. I'm going to write it as a negative radical 3 over 2 over 2. To be able to put the numerator together, I'm going to turn this 1 into 2 over 2. So now this becomes the radical, they're really cool, of 2 minus radical 3 over 2 over 2. This is the numerator, there's your denominator. Technically, this is a fraction, so that means I can multiply by the reciprocal. So this becomes 2 minus radical 3 over 4. The square root of 4 is 2, so this becomes 1/2 because it's in the denominator, square root of 2 minus radical 3. And then I would report my answer, and you could either do 150 over 2, or you could say that it's the cosine of 75 degrees. So the thing that's important to remember when we're using our half angle formulas, we're going to double the angle to create a special. And so then when I use the formula, I have to choose which of the plus and minus signs to use, and that's going to come from the original angle. Once I get on the inside, by the time I get down to my answer, I'm going to have what's called a nested radical. And that means that it's a radical inside a radical, and we're going to go, ooh, that looks cool, I look smart, and we're going to call it good. Alrighty, that is it for today. I will see you soon.